Okay, good morning and wish you a happy new year. So, shall we start now?
Okay, so happy New Year, sir.
Yeah, okay. So, actually, last time, so I believe like you can see the screen. So, we had a discussion how to get the differential equation for this given circuit and how do we can solve it for this force response and natural response. For example, if you just apply Kirchhoff voltage law for this, so we know that there is a inductor here, so you can simply write the voltage across the inductor as L times the derivative of the current. So we have 2 Henry and the current derivative. So then we have this 2 ohm resistor. So the drop across this 2 ohm resistor is 2 times the current. So then we have a capacitor. So then the drop across the capacitor would be 1 over C integral of this current. So 1 over C is 10 integral from 0 to T. So this I tau d tau plus the initial conditions of the capacitor. So this is the total drop across these individual elements and which is equals to 15 cos 2t. So then, so we have derivative terms and integral terms. So to avoid this integral term, so we can simply take the derivative with respect to t to the entire expression. So then this becomes a kind of a form like d squared it to dt squared plus dito dt plus phi it, which is equals to minus 15 sine 2t. So then by looking at this one, this is a kind of a second order differential equation. So here, like if you carefully go through these individual terms, so you can see that so you have a second order derivative here. So this it's minus 30, but you have to factor 2 here. So once you divide it by 2, then it basically reduces to the d squared plus d plus phi it equals minus 15 cos sine 2t. Okay. So then, so this is the second order differential equation in general. So we'll go through how we can solve the second order differential equation. But easily you can find the natural response, force response. So to evaluate the force response, so to evaluate the force response, IFT, so we can propose a kind of a trial solution as A cos 2t plus B sine 2t. So if this is a trial solution for this particular differential equation, so if you substitute this component, if you substitute this to the original differential equation, so it's basically satisfied. So by substituting, you can find A and B. So if you substitute to this differential equation, can find A and B. So this is the way we found the force response for any kind of a differential equation, whether it's a first order or second order. If you have a force term like this, a kind of a sinusoidal excitation or sinusoidal cos or sine term, so we use this as the very generic trial solution. So keep in mind, so this factor should be appear here. So you can't simply replace this your trial solution with cos 3t and sine 3t, because so we argue in the previous session. So this is your force term, this is your force term. So the force term is basically aligned with the external sources. So you connect to the circuit. So it's basically aligned with the external sources you connect to the circuit. So the external circuit, external source is basically having a frequency of 2t. All right, omega equals. So this is like this is 2 phi ft. So this is 2 phi ft or else omega t. So omega t equals 2. So ideally this omega equals 2 radians per second. So we basically connect the external sinusoidal excitation with the angular frequency of 2 radians per second. So then definitely this force term also has the same angular frequency. So that's why we have sine, but the angular frequency here also it's a 2. So then the proposed force response or the trial force response again have the same angular frequency. So that's why this 2 comes in front of t. So then ideally it should be a cos 2t plus b sine 2t. So if you have sine 4t here instead of 2t, if you have sine 4t, so then this trial solution would be a cos 4t plus b sine 4t. So keep in mind, so it's basically aligned with the angular frequency or the frequency of the source we basically connect. So this is the way we try first to evaluate this A and B and the force response. So then we argue that rather moving with the 15 cos 2t, so we can basically replace the source with its exponential component. So then what we can simply do is we will simply replace it e to the power j 2t. So then instead of this source, instead of 15 cos 2t, so we'll create a scenario where we have a kind of a complex exponential as a source. So then basically we can replace this 15 cos 2t with this one, 15 e to the power j 2t, and evaluate the force response basically aligning with this 15 e to the power j2t. So then take real of this force response. Why it's real? So this cos 15 cos 2t is actually real component of this one. 15 cos 2t equals real part of 15 e to the power j2t. So therefore we basically take the real component of this, whatever the force response we obtain for this exponential source. So this is the second way, because if we replace this cosine term with a source of exponential, we found that we need to evaluate a single constant. Because so the idea here is, if you have this cosines as a force term, so your trial solution would be something like this: a cos 2t plus b sine 2t. So if you have this exponential function as a force term, so we can simply use our trial solution as a kind of a constant e to the power j 2t. So here you need to basically find out both a and b, but in this case you need to find this k. So finding two constants is comparably difficult than finding a single constant. So then what we propose is, instead of this cosine or sinusoidal excitations, we basically replace it with corresponding complex exponential and evaluate the force response and take the real or imaginary component according to the exact source which we basically connect. If it is a cosine, we take the real component of the force response we ultimately get. If it is a sine component, if your source is a kind of 15 sine 2t, so we'll simply pick the imaginary component of the ultimate force response. So this is the way we move forward. So the second would be better, because we can easily find out a single constant. If you move with this sinusoidal excitation, so you basically need to find both a and b. But if you replace the source with the corresponding exponential, so you can easily find a single constant, which is k here, and uh, reach to the force, your ultimate force response easily. So this is the basics we discussed last time. So now we want to move to next level. So it's something like that. So I believe like you have kind of idea about this. No. So next we'll move to this phasor circuit. So next we'll move to the phasor circuit. So before we move to the phasor circuit, so we should identify how we can represent these capacitors and inductors in phasor domain. So let's go through this one. So we know that for inductor, so this is the relationship. The induced voltage across the inductor is basically equals to the L times the derivative of the current. So this is the fundamental formula which describes the relationship between voltage and current. So let's assume that the current flow through the inductor is simply following this format. Im e to the power j omega t plus theta. So this particular current has a angular frequency of omega and an initial phase shift of theta. So this is the angular frequency and this is actually initial phase shift, initial phase. Okay. So if this is the current Im e to the power j omega t plus theta, so we can evaluate the induced voltage across this inductor. So then VLT equals L times the derivative of this one, derivative of this current, Im e to the power j omega t plus theta. So the derivative of this current. So this theta is actually independent of t. So we can treat this e to the power j theta as a constant. So then we can simply bring this Im e to the power j theta component out from this derivative. So then this becomes L Im e to the power j theta, and take the derivative of e to the power j omega t. So then we have j omega here and e to the power j omega t. So this is the derivative of this e to the power j omega t. So this is the uh, constant we treated separately. So then we can basically simplify this like this: j omega L. Then we have Im e to the power j omega t plus theta. Okay, so this is the current flow through the inductor, Im e to the power j omega t plus theta. So what about this component? So this is equals to the voltage induced across this inductor, VL. So V equals I times a kind of a component. So if it is a resistor, we know that this would be the resistance of the resistor. V equals I times R. So similarly, we can define a term called impedance. So then this is the impedance of the inductor, ZL. So this is the impedance of the inductor. So then from this equation, we can basically get the impedance of the inductor as j omega L. So L is the inductance of the inductor. Omega is the angular frequency of the source. And J basically represent the complex domain. So then this the impedance of the inductor basically a kind of a complex number. So this is a kind of a complex number, and it depends on, it's a function of omega and L. So omega is the frequency of the source. So then from this expression we obtain here, we can basically argue that the impedance of the inductor is basically depend on the frequency of the source, omega. So then from this, so we basically can argue what happens if omega equals 0 and what happens if omega goes to infinity. So what about omega equals 0? So then ZL, the induced impedance of the inductor, converge to 0. If your omega equals infinite, so the induced impedance is actually goes to infinity. So ideally, impedance 0 means we can replace the inductor as a kind of a short circuit element. So then the 0 frequencies inductor act as a short circuit element. So as the zero frequency means, so if we argue that zero frequency means DC signals, DC signals. So then inductor act as a short circuit element for DC quantities. Inductor act as a short circuit element for DC quantity. So this is the conclusion we can simply get it from this one. For omega equals 0, it's short circuit. So omega equals 0 means DC component. Similarly, we can argue for omega equals infinity. So you will ended up with infinite impedance. So it means this is kind of open circuit element. So you can't see any kind of a current flow through this particular element because the impedance or kind of a resistance is infinite. No current flow through this branch. So then it means, so omega equals infinity. In practical scenario, we can assume that this is for high frequency signal. So then for high frequency signals, we can basically assume that inductor act as a kind of an open circuit element. So these are the two conclusions we can made out of this impedance of the inductor. If it is a DC signal, your inductor basically act as a short circuit element. If the signal is having a higher frequency, so you can treat this inductor as a kind of an open circuit element. Okay, so these are the two conclusions we can easily made out of. So if it is a kind of a infinite frequency, so it basically can treat it as open circuit. So infinite frequency in practical domain, so we can assume that it's a high frequency signal. So these are the conclusion we can made out of. So then we found that the impedance of the inductor is j omega L. So then like resistor, you can simply replace the inductor with this component if you know the frequency of the source. So for example, if this is the case, so now we know that the source is 15 cos 2t. From this expression, we can easily identify your omega is 2 radians per second. So then this 2 Henry inductor can be replaced with J, omega is 2, L is again 2. So then it's like 4J. So this 2 Henry inductor can be easily replaced with 4J. So like in 2 ohm, so the induced impedance of the inductor for this particular source is 4J ohm. Okay. So this is the way we can simply replace the inductor using its impedance. So I need to, yeah. So from this one, see like, so we have a J component here. So if you have a J component, we can replace this J with e to the power J5, 5 by 2. So let's assume we have this complex exponential term e to the power J5 by 2. If you apply Euler transformation, so this can be replaced with cos 5 by 2 plus J sine 5 by 2. So we know that the sine 5 by 2 is actually 1. Cos 5 by 2 is actually 0. So then e to the power J5 by 2 can be simplified to J. So if you have J term in your expression, you can basically replace this j term with this phasor, e to the power j 5 by 2. So then if you substitute it here, so you have v as d, because j can be absorbed to this exponential. So we have omega L I m e to the power j omega t cos theta cos 5 by 2. So then how do you evaluate the voltage induced across the inductor? So how do you obtain the value of this voltage? So we basically multiply the current magnitude, the magnitude of the current. So this is the magnitude of the current, Im, with this omega L factor. So we can simply say that, so the magnitude of this VLT equals omega L Im. So the magnitude of the current is this, magnitude of the current. So it's just multiply with this factor omega L. So then you can get the magnitude of the voltage. So keep in mind, so if you have this current, you can easily capture the magnitude of the current, and if you multiply it with the source frequency and the inductance value, you can easily get the magnitude of the voltage. So what about the phasor? With respect to current, so the phasor is 5 by 2. So this is the current phasor, the phasor of the current waveform. So then we can argue that phasor or the angle of VLT equals 5 by 2 with respect to the current phasor, phasor of this current. Okay, so we can, by looking at this expression, we can simply say that the magnitude of the voltage is actually the product of omega L and the magnitude of the current. And the angle of this voltage is 5 by 2 with respect to the angle of the current. So if we replace this Im e to the power j omega t plus theta with the kind of phasor notation, so we can, so if we replace this component, we can simply claim that this is equals to Im, an angle of 0. So it means like the, so if you push it to the 0 degrees, so it means, so everything is measured with respect to this omega t plus theta. So with respect to omega t plus theta. So that's why the angle is 0. So if we measure the quantities with respect to this current, we can represent this current as Im with angle of 0. So this is the magnitude component. So this is the magnitude, and this is the phasor with respect to this initial phasor of this current, omega t plus theta. So there won't be any additional phasor for this current. So we basically absorb this omega t plus theta as a reference. So with that reference, so your additional phasor is 0. So with respect to this Im an angle of 0, we can simply give the voltage as omega L Im. So this is the magnitude of the voltage, and the phasor is 5 by 2 with respect to the current phasor, omega t plus theta. So from this, we can basically take these two. omega L Im is the magnitude of the voltage. So this is the phasor of the voltage. Okay, so if you draw this phasor diagram, so it's something like that. So Im theta, if you draw the Im theta, so it's like that. So this is your Im, an angle of 0. So this is your current phasor, capital I with bold. So this is the current phasor of the inductor, Im. So with respect to this current phasor, so the induced voltage has a phasor of this. So this is your voltage phasor, VL. So the magnitude is omega Lim and the angle is 5/2. Okay. So then, so see, like always, the current and voltage phases of this inductor is orthogonal. So the phase difference is 5/2, orthogonal. So this is orthogonal, 5/2 different. So always the induced voltage and current has a phase difference of 5/2, 90 degrees. So that's why we simply say that voltage and currents are basically orthogonal. And at the same time, so you can see always your voltage is leading the current by 90 degrees. So this is VL is leading the IL or the current by 90 degrees. So your VL is basically leading the current by 90 degrees. So always VL is having additional 5/2 phase shift with respect to current. So then from this phasor diagram, you can simply draw the phases of the current and voltage across the inductor. For example, so let's think. So some in one question paper, it's marked this is your current flow through the inductor. So what about the voltage then? So you can easily mark the voltage which is basically perpendicular for this. So this is the induced voltage. So for some cases like, so this is your current. So then this should be your voltage. Is all the time your voltage should lead the current by 90 degrees. So then across the inductor, so this is the phasor relationship between voltage and current. Always your voltage is leading the current by 90 degrees. So then based on that, if you know the direction and the magnitude of the current phasor, you can easily draw the corresponding induced voltage across the inductor using this simple concept. Always your voltage is lead the current by 90 degrees. So this is the simple conclusion we can made out of this simple equations. Okay, so hope it's clear. So if you have anything, just ask me. So similarly, you can do this calculation for the capacitors as well. Okay, so I don't want to go through this same derivation for the capacitor. So what I want is to summarize this one. So we have inductor and a capacitor. So this is IL, VL, IC, VC. So this is the fundamental formula for inductor. Similarly for the capacitor, so this is the fundamental formula, C times the derivative of the voltage. So then we found that for inductor, so the induced impedance is J omega L. Similarly for the capacitor, the induced impedance is 1 over J omega C. So by looking at this one, we claim that for omega equals 0, we have 0 impedance. For this case, omega equals 0, we have infinite impedance. So then we claim that inductors are act as short circuit element for DC, but capacitors basically act as open circuit elements for DC. Because so the impedance term, the omega is happy in the denominator, so omega is equal to 0, so then the induced impedance goes to infinity. So inductors act as short circuit element in DC domain, but capacitors act as open circuit element in DC domain. Similarly, for higher frequencies, omega for infinite values, so this becomes infinity, omega infinity, ZC goes to 0. So from this we can claim that this is act as open circuit element for high frequency. Capacitors act as short circuit elements for high frequency because the induced impedance is 0. So then we can claim that for this case, if the phasor is 0, the voltage is almost perpendicular. VL is actually omega L Im, an angle of 5/2. Always we have 5/2. Similarly for the capacitors, so this is your VC, Em, angle of 0. So the other way around. So current is basically the simple. So here, this is your current, IL. So this is the current and this is your voltage. For inductor, always V is leading the current. But for the capacitor, so I is leading always the voltage. So this is the simple difference. So this is the summary for inductors and capacitors. So if you want to replace the entire circuit with impedance, so you can use this formula to replace the inductor and this to replace the capacitors. If you are dealing with a DC quantities, so you can treat inductor as a short circuit element and capacitor as open circuit element. If you are basically dealing with higher frequency signals, so you can treat the inductors as open circuit elements and capacitors as short circuit element. So if you are working on phasor domain, so you can simply draw the voltage phasor of an inductor like this. Always it's lead by 90 degrees And if it is a capacitor in phasor domain, always your current is lead by 90 degrees with respect to the voltage. So this is the simple summary behind that. So if you have any questions, so you can bring it to the forum. No? Okay. Now we know that if you have inductors, so you can simply replace the inductor with this. So this is the impedance. So if you have capacitors, so you can simply replace the impedance of the capacitor using this. So nothing else. Okay. So can you convert this circuit diagram, convert this circuit to a phasor circuit? So can you convert this circuit to a phasor? So how do you convert it? Okay. So this is the way we can convert it. So this is the circuit. So we have a source of 15 cos 2t. So in general, any kind of a cosine and sinusoidal waveform can be written as this kind of AM. So this is the peak amplitude and cos omega t plus theta. So this is the initial phase shift, initial phasor, and this is the peak amplitude. Any kind of the sinusoidal or cosine signal can be replaced with AM cos omega t plus theta. So theta is the initial angle and the omega is the angular frequency, and this is angular frequency, and AM is the peak amplitude. So by looking at this, we can simply claim that AM peak amplitude equals 15, omega equals 2 radians per second, and theta, the initial phase angle, is 0 degree. So then we can convert this, to a phasor like this, amplitude and the initial angle. So then this is basically replaced with this 15 and the angle of 0. So that's why it's here. So then we can simply replace the inductor and the capacitor. So we have a 2 Henry inductor. So we can simply replace this inductor with its impedance J omega L. J omega equals 2, L equals 2. 4J. See, it's 4J. So then we have this 2 ohm resistor, no need to replace it. So the value or the impedance is as it is. So we have 1/10 farad capacitor. So the impedance of the capacitor is 1/j omega c. 1/j omega equals 2, c is 1/10. So then this is like 5/j. Or else you can bring this j component to the numerator, so then it becomes minus 5j. So see, so then we can basically replace this time domain quantities, time domain to phasor domain. So we convert this time domain quantities to phasor domain. So then what happens to the circuit? So instead of this real value, so you basically ended up with the impedance, total impedance as a complex number. So how do you evaluate the total impedance of the circuit? So those elements are series connected to each other. So then if it is a series set of impedance, you can just sum this up. So like in the resistors, if you have series set of resistors, you can just add those values to evaluate the equivalent or the total resistance. Similarly, for impedances, if they are in series, you can just add those values. But keep in mind here you have both real and imaginary components. So you cannot just add these values because those are not only real. So you have real and imaginary components. So you have to add this real and imaginary components separate. So here we have a real component of 2 come from this, and imaginary components we have 4j here, and here we have minus 5j. So these 2j minus j. So this is the total impedance of the circuit. So this is the total impedance. ZT. So you can use whatever the notation. So ZT, for this case, it's a total impedance. So these elements are connected in series. You can just add these impedance together, but they are both real and imaginary. So we basically add the real components together and imaginary components together. So then the total impedance would be 2 minus j. So then we know the total impedance. So this is total impedance is 2 minus j. So we have a source of 15 and angle 0. So how do we evaluate the current? So we know the resistance, we know the voltage, we need to find the current. So you can easily find the current in a phasor format. So voltage divided by the impedance. So this is the voltage. So this is the voltage and this is the impedance. So this is just the voltage divided by impedance. Nothing else. But once you write this expression, see, like the voltage is basically in the phasor format, I mean r theta format, but the impedance is basically in rectangular or Cartesian format, a plus jb. So this is in r theta form. This is in a plus jb form. So we need to convert this a plus jb also into r theta form or polar form. So how do you convert this into r theta form? So you can, you know that if it is a complex number which is in a plus jb or Cartesian or this real and imaginary component, so you can immediately convert it into this r theta form. So r, or the magnitude, is actually square root of this real plus imaginary. So square root 5. So the angle is theta. So the value of this theta is tan inverse minus 5. Okay, because here the sine component is minus 1 over root 5 and this is like 2 over root 5. So ultimately if you just add it, so it gives like tan inverse minus 1. So hope you can convert this any complex number which is in real plus j times imaginary to its polar form. So believing that, we can simply say that this 2 minus j can be converted into a phasor form like square root 5 and the angle of theta. So the theta angle is tan inverse minus half. So you just then substitute it here. I'll just remove this one. Now we convert this ZT to minus j into root 5 angle of theta, where theta equals tan inverse minus half. Okay, so the current is actually 15 0 divided by root 5 angle theta. So how do you solve this one? So we can simply treat the amplitude and angle separately. 5 divided by root 5 equals 3 root 5. And here 0 and theta. So the angle is minus theta. And theta actually tan inverse minus half. If you want, you can take this minus out and take this minus theta as tan inverse half. So then, so this is again can be written with the positive angle with theta degrees, and theta is actually tan inverse half. Okay. This both is fine. So now the current phasor is in the form of this. So this is the magnitude, this is the amplitude or magnitude. So this is the phasor with respect to the voltage, with respect to this. Okay, always this phasor is with respect to this current, because so we know that the this current is depends on the source you connect. So then all the way time, so the current phasor is with respect to this one. So that's why it's like 15 angle 0. So then the voltage source is actually in the form of 15 cos 2t. So we convert it like this, 15 angle 0. Now we obtain that current as 3 root phi angle of theta with an inverse half. So how do you convert this back to a time domain? So 15 is the amplitude, angle is here. So you can simply convert it to time domain by this. So you can put the magnitude as it is. And this theta is basically with respect to this cos 2t. So you can simply write this cos 2t plus theta. So this is the current response. So this is the current phasor, and everything is basically with respect to this. So then we can, once we get the phasor value, so you can easily convert back to time domain, So this is the magnitude. So we just brought it here, and this is the phase shift with respect to this. So this is basically come from cos 2t. So you can just put cos 2t and plug this additional phase here. So this is very simple. So then how do you if you are given a time domain circuit, how do you convert it to into phasor? So you can convert the sources like this, magnitude and the initial angle. For example, so let's have you have a source like this, 2 cos 3t, and the other one 2 cos 3t plus 5 by 3. So you have two sources. One is having a 0-degree initial phase shift. So the other one is having a 5 by 3 initial phase shift. So here 0 initial phase shift. So here 0 initial phase shift, initial phase. Here 5 by 3 initial phase. So if you convert this 2 cos 3t to phasor, you can simply come up with this. Here you can have two options. One is this. So the other one is this. So for this case, you can have this 2 an angle of 5 by 3 by treating this as an initial phase. Or else you can basically absorb that 5 by 3 also into the 3t omega t component and simply say that your initial phase shift is 0. So in this case, everything is with respect to 3t. Here, so for this case, this is with respect to 3t. Here, this is with respect to 3t plus 5 by 3. So that's why it's 0. Okay. So if you want something converted back into time domain, for example, if this is a source, if you evaluate the voltage or current phasor, and if you want to convert this, so whatever the values appear in this scenario back to time domain, so you basically take the amplitude and add cos 3t and whatever the angle coming from this phasor. So let's assume like you have this phasor. So if you evaluate it and find the current as AM and angle of theta, so if the source is converted into phasor domain like 2 and angle of 0, So then this is basically AM cos 3t plus theta. So this additional angle appear here because we take this 3t as a reference. So assuming that no initial phase. So if you treat the same to here, and if you want to add the or convert this current into time domain, so this becomes AM cos. So the whatever the angles basically evaluate hereafter is considering this 5 by 3. So then this is again becomes 3t plus theta. Because this 5 by 3 is already counted into the calculation. So the whatever the theta appear here is basically embed this 5 by 3. So then you don't need to worry about this 5 by 3. So the everything is with respect to this 3t. So then AM cos 3t plus theta, where this theta is coming from this one. So you can easily get this. So this theta itself, consider this 5 by 3 initial, because we use this 5 by 3 to the phasor. So then everything basically take this 5 by 3 into account. So then you don't need to worry about this 5 by 3. So it's already embedded in this theta. So then everything is with respect to 3t. So you can simply say that AM cos 3t plus theta. If you convert this here, so this becomes AM cos, because we take the reference as 3t plus 5 by 3, so you have to put 3t plus 5 by 3 here and then theta. Because in this case, the reference is actually 3t plus 5 by 3. So you can just bring the amplitude and phasor values. But keep in mind, in this case, you have this term should be there. Because everything is basically with respect to 3t plus 5 by 3, not only for 3t. But for the other two cases, we consider the reference point as 3t plus 0. So that's the difference between this additional non-zero initial phase shift. How do we convert into phasor and manage to convert back into time? So then the summary is actually, if you are getting a time domain circuit, you can simply convert it into the phasor domain to evaluate the force response basically. You can't evaluate the natural response from this one, because natural response is simply because of this initial condition. So then definitely you have to solve the differential equation. So we'll keep that part aside and think of or focusing on force response. So the initially we tried with this sinusoidals and replaced the sinusoidal with the more general force response, A cos theta plus B sine theta, and find out A and B and obtain the force response. So then we replace this cosine and sine terms with its corresponding complex exponential and propose a trial solution like k e to the power j theta and find k and obtain the force response. Now we try to convert this time domain circuit to phasor domain. So sources are basically converted into phasor form, and inductors can be converted into its impedance like j omega L, and all capacitors can be converted it into 1 over j omega C, because it's the impedance of the capacitor. So the resistors, the value of the impedance is equals to the resistance value. So there won't be any change for that particular value. So then your time domain circuit can be converted into phasor. So you have magnitudes and angles, and most of the impedance are both real and imaginary. So then you can treat it as a kind of a resistive circuit. So you can apply Ohm's law by treating this impedance as a kind of a resistance. So if those elements are in series and parallel combination, you can use this very fundamental rule of simplifying this series and parallel combinations and find the ultimate or the equivalent impedance in the form of complex number, a real plus an imaginary component, and then just divide the voltage with that impedance, or if you just multiply the impedance with the current, you can get the voltage. So after that, if you convert it to the phasor circuit, so nothing new for that. So whatever the simple electricity theories can be easily applied. So the Ohm's law is still valid for them. So you can just apply V equals I into not R, it's like Z. So then it's like V equals I into Z. So this is impedance. So very simple. You can easily find voltage and current according to that. So if you want, we can have one more example. Yes. So this is one more example. So this is already in your slide set. This is exercise 5. So we have a source of 5 cos 3, 5 cos 3t. So how do you convert it to phasor? So first identify the amplitude. So the amplitude is equals to 5. Angular frequency is 3 radians per second. Initial phase shift is 0. So you can just convert this into 5, 0. And you know that this is this, the angular frequency is 3 radians per second. So then the rest of the impedance and capacitance can be converted according to that. So we have 1 Henry inductor, 1 Henry inductor. So once you convert it to the impedance, J omega equals now 3 radians per second. L is 1 Henry, so this becomes 3J. So we have 1 over 9 farad capacitor. So you can just convert this C 1 over J omega. C is 9. So it's like 3 over J. If you bring this J to numerator, so this becomes 3J. Okay. So then the simple I1 can be replaced with bold I1 capital, and the simple I can be replaced with bold I. So this source is basically replaced with 5 0 like this, and 1 ohm is here, nothing different, 3 ohm is here, and this inductor basically, so this is replaced with 3J, and this capacitor is replaced with minus 3J. So it's like this. See, so we have 3J here, minus 3J. So nothing happened to this one and this one. And this simple I1 is replaced with capital I1, simple I, base I. So the source is converted to 5 angle 0. So then if you want to evaluate this I, so you can simplify and find out the I1, because now this capacity is in parallel with this 3 plus 3, this impedance. So what is the effective impedance for this? So this is like 3 plus 3J. So this 3J and 3 ohm are in series. So you can just add these two values. So, but they are both real and imaginary. So I had to treat both real and imaginary separately. So then ultimately it's like 3 plus 3J. So then you can have this combination. So this 3 plus 3J is parallel with minus 3J. So you can just consider the equivalent with the parallel combination. So that parallel combination is in series with 1 ohm. So then you can simply evaluate the ultimate impedance. So according to the slides, it's like Z total equals 4 minus 3J. Okay, so then this is basically simplified to this form. I will put this. So you have a kind of element having an impedance of 4 minus 3J and a source of 5 angle 0, and this is I1. So you can just apply this Ohm's law. So this I1 phasor can be obtained through 5 angle 0 divided by 4 minus 3J. So then you have to convert this into R theta form. So once you convert this, this becomes 5, an angle of theta. So the theta is actually tan inverse minus 3 over 4. So then I1 is actually 5 angle 0 divided by 5 angle theta. So this is just the magnitude is 1, angle is minus theta. So this theta equals tan inverse minus 3 over 4. So from this you can evaluate I1. So if you know I1, you can simply evaluate I by applying current divider rule. So you have I1 flow into the node, and it's basically split across this branch and this branch. So you can just put the current divider rule and find out the exact impedance or exact current flow through this I. So keep in mind, so now this analysis is basically on complex domain. So you cannot treat these values as just a real numbers. So you have to refresh your complex analysis theories and use those theories to solve these complex numbers. So you have to convert into rectangular or polar or vice versa. And you cannot just add these components. So because we have real and imaginary components separately, you have to treat them separately. So if you have these ratios of complex numbers, you cannot just divide these two. You have to sometimes multiply with the reciprocal or the conjugate and simplify. So those theories you study in complex analysis should be simply applicable here. So from this onward, it's something related to mathematics. So you can use the mathematics knowledge and come with the exact value, but keep in mind, so ultimate value should be in phasor. Phasor means a kind of a magnitude and angle. So then whatever the values in the rectangular form, A plus JB form, should be converted into polar and simplify and take the value as a R theta form, in R theta form. So once you take this in this R theta form, you can simply convert it into time domain, because now this everything is with respect to 3t. So you can simply say that, so the amplitude cos 3t plus this angle. So this is here, and this is the reference, and this is the amplitude appear here. So nothing else. Okay, hope it's clear. So the other thing is this. So what happens if you have different sources? So I'll take one example. This refers basically the exercise 11. Refers the exercise 11. See, so we have one source here, it's a voltage source, and there's another voltage source here. So one is actually 12 cos 2t. So the other one is 5 cos t plus 45 degrees. So if you convert this into phasor, you can simply say that this is equals 12 and angle of C. What about omega? So this here, omega is 2 radians per second. If you convert this into phasor, so you can either use this form or else you can either use this form. But for both cases, omega equals 1 radian per second. So is there any impact to the circuit? Yes, because if you convert these capacitors and inductors to its corresponding impedances, here you have to consider the value of omega as 2. For this case, you have to consider the value of omega as 1. So then you cannot do it in a single block. So then what we can simply do is apply superposition. So apply superposition theorem. So it means take one source at a time and evaluate the response, and then later on you can add the responses together to get the final response. First take the source 1, 12 cos 2t. So you can take 12 cos 2t first and convert everything into phasor. So then it's something like that. So see, so we convert this circuit. So this is a voltage source, so you can drop it because in the superposition, what we simply do is take one circuit or consider one circuit, assuming that the rest of the circuit's impact is 0. So the voltage source, if you want to make the impact of the voltage source to 0, so let the voltage to 0. So if you set the voltage or let the voltage to 0, so there won't be any voltage drop, then this U voltage source can be replaced with the short circuit element. So that's why we basically replace it with the short circuit element. So then you can basically convert this impedance, the inductors and capacitors, to its corresponding impedance by assuming that omega equals 2 radians per second. See here we have 1 over 2 farad. So once you convert into the impedance with omega equals 2, so it's like -1. Here you have 1 Henry. If you convert it to impedance, it becomes 2J. So then you can analyze this circuit and evaluate the voltage of V1. So then you can consider this next circuit, 5 cos t plus 45. So then, and then you can simply convert the circuit into phasor. So then it's something like that. See, in this case you have this source. Now you have this 5 and 45. So we just convert it to 12 to 0. Here it's 545 and omega equals 1 radians per second. So see, like your inductor is J and capacitor becomes minus 2J. So then you can simply take V2 and evaluate it, and you can just add this V1 and V2 together. So keep in mind that V1 and V2 are in phasor domain. So if you add it, either you have to convert into rectangular form, A plus JB form, or else you can convert this V1 and V2 to time domain and then add it. So then you may use this trigonometric formulas to simplify. So both are possible, but like, so that for example, like if V1 is like A1 theta 1 and V2 is actually A2 theta 2. So you cannot simply say that the ultimate angle is theta 1 theta 2. So this is wrong. So keep in mind, if you want to add it, either you have to convert it to r theta form, sorry, not r theta, A plus J beta or Cartesian form or rectangular form, or else you can convert the V1 and V2 phases to time domain and then add it. So you cannot add these phases directly. So keep in mind that point, otherwise nothing different compared to the previous. So for this case, if you have different sources, but keep in mind different sources with different frequencies. Huh? So different omega. So if you have the same omega, you don't need to do this superposition, because it's basically because the impedance of the circuit remains as it is, so you don't need to worry about if the multiple sources are in same angular frequency, same omega. So if you come up with the circuits where you have multiple sources with multiple frequencies or different frequencies, then only you can apply the superposition and evaluate the components, or evaluate the values separately and sum it up at the end. So this I am referring this exercise 11. So you can go through this exercise 11 and see how we can do it. Okay, so for today, so we can stop at this point. So if you have any questions, you can raise it. If you don't have any questions, so we can wind up the session. Yes, you have one more question. Yes, for this previous records, actually, so with this new developments, all these YouTube links basically drop from the previous. So what I can do is I'll share these all links to your batch representative, so he can share basically to you. So I think it's the easiest way. So whatever the PDF files are there, PDF or presentations are there, but so the embedded videos like YouTube videos, so basically with this migration, so they simply vanished off. So I'll share those stuff. So if you don't have any questions, so next time we'll move with this phasor circuits, I mean the phasor diagrams. Now we did this phasor circuits, so next time we'll discuss one or two examples for phasor diagrams. So then we'll move to the second order differential equation. Okay, see you then. So